Hi again. This is the first video to go along with section 12, which is on applications of linear functions. So the first problem here is suppose that it costs $5,000 to start up a business selling snow cones. Furthermore, it costs 50 cents per cone in additional costs. Then the cost to make X snow cones is given by Y dollars, where Y equals 0.50X plus 50 or 5,000. What are the units on input? Well, this takes us back to the beginning of the semester where we looked at the difference between input and output. Input is the thing that has to be known first, and output is the thing that you're trying to measure. So in this situation, pretend this is your business, okay? You want to sell snow cones. What does your business depend on? Well, you have to sell snow cones in order to make any money, right? So the snow cones are going to have to be your input. So let's fill that in. And the dollars or the profit is going to have to be your output because that's what you're trying to measure. In this case, it's not your profit, it's your costs. How much does it cost you to make and sell these snow cones? So when 100 snow cones are made, the cost is $5,050. Express this as a point. Well, this is why it's so important to know your input and your output. Your X here represents snow cones, and your Y is representing dollars. And so all ordered pairs are input comma output, or X comma Y. So it's going to be the point 100 comma 50/50. When the cost is $6,000, the number of snow cones made is 2,000. Express this as a point. Well, this time the information is given in the opposite order, but we know that it always goes input comma output, and the input is still snow cones. So this ordered pair should be the point 2,000 comma 6,000. What is the slope in this equation? Well, let's take a look up here. This looks very much like y equals mx plus b, doesn't it? So m is this 0.50. Did we see 0.50 anywhere else described in the problem? Yeah, we saw that it's going to cost us 50 cents per cone to sell snow cones. So the units are going to be our output units over our input units. Rise over run, change in y over the change in x. So this is going to be dollars per snow cone, which makes sense because it's described up above as 50 cents per cone. So that's actually a clue. That word per is a clue. We're looking at slope as a rate of change here. It's the rate that we are getting our cost incurred for our business. So when we see the word per, or maybe a phrase for every or for each, those are slope indicators. Those are rate of change indicators. This was described as 50 cents per snow cone. I also could have said that it costs 50 cents for every snow cone made. I also could have said it costs 50 cents for each snow cone made. So again, all of those phrases are going to indicate some sort of constant rate of change, which is what indicates a slope. Now let's talk about f. What is the y-intercept in this equation as a point? And then use a sentence to explain what it means in the problem. So let's go back up and look at the equation again. The equation was y equals 0.50x plus 5,000. If I compare this to y equals mx plus b, 50 or 5,000 is in place of the b. So we know that b represents our y-intercept. So the y-intercept here will be the point 0, 5,000. Now the question is, what does that mean in the context of this problem? Well, what did it cost for me to start up my business? Just to start my business, it costs $5,000. Isn't that what was described at the top? So if I sell no snow cones, if I make no snow cones, it still costs $5,000 to run the business. So that's what we're going to put for our explanation. When I make 0 snow cones, it still costs $5,000 for the business. And again, this is just describing the input and describing the output. Our last task here is to graph this equation and label everything. Now, this is where domain and range is going to come back into play. So you got to think back a little bit. Domain is all the x values or the input values that make sense in the problem. Does it make sense here to make negative snow cones? No, it doesn't make any sense to make negative snow cones. The output here is the cost. Well, because this is looking at all costs, we're not going to have a negative cost. So that's not going to go negative here either. And so we don't need to show any negative quadrants. We can simply show the positive quadrants. So if I were to make the graph here, I'm going to draw my axes starting from the corner because I'm only going to care about positive numbers, okay? The next thing that we need to think about is our increments. Well, I can sell 1, 2, 3 snow cones, or I can count by 5s, or I can count by 10s. Because this is one of our first examples, let's just see what happens for each snow cone. So I'm going to label this snow cones because that's my input. So we're going to label our input and we're going to label our output, which is money. And then we have to think about increments. So my snow cones, I am just going to count by 1s just to see what happens. Okay. For my output, notice that we start at $5,000. There is no way I'm going to be able to count to $5,000. So that's where you put either a sharp squiggle or these 2 hash marks to show that you're skipping values. And then we can start counting at 5,000. And then we can say, okay, this is 5,001, this is 5,002, 5,003, and so on. Now remember, we're charging 50 cents per snow cone. So when I sell 1 snow cone, well, first let's go back to 0. When I sell 0 snow cones, I already know that it costs $5,000 to have the business. When I sell 1 snow cone, I only go up 50 cents because it only costs 50 cents. When I sell 2 snow cones, that's another 50 cents. So I go up to the next dollar. And then every increment is up 50 and over 1, up 50 cents and over 1. So we have a dot here, we have a dot here, we have a dot here. And every time I'm going up another 50 cents for 1 snow cone. Up another 50 cents for 1 snow cone. And then we can see that we're drawing a nice line. And so I start with the 5,000 and I show that that's going to be my trend. Notice how there's no arrow on this side because you can't go negative. That's why we didn't draw this quadrant. So this is the lowest that we're going to go. So now let's go to another example. So this is actually in the notes on linears, which is not in any particular section on Blackboard. This is kind of on its own in Blackboard. It's notes on linears. And at the very end of this document are some word problems. So that's what I'm showing here. So in problem 1, it says an air conditioner, should be air conditioner, is turned on when the temperature inside a house reaches 80 degrees Fahrenheit. For every 1 hour that passes, the temperature in the house decreases by 2 degrees. So let's see if we can make a table out of that information. When no time lapsed, how hot was it in the house? When no time lapsed, the house was 80 degrees. What happened after 1 hour passes? After 1 hour passes, the temperature decreases 2 degrees. So if I go from 80 and I decrease 2, I'm now at 78 degrees. What happens when I increase another hour? When 1 more hour passes, I lose 2 more degrees, so I'm at 76 degrees. When 1 more hour passes, I'm at 74 degrees. When another hour passes, I'm at 72 degrees. When another hour passes, I'm at 70 degrees. Now, this will eventually have an end because you're not going to keep cooling your house until, it's freezing in your house. So this will have a boundary, but for these purposes, we're only looking at the pattern. So if we take a look at this pattern, and I ask, what is the slope here? We can do one of two things. We can either calculate the slope as the change in y over the change in x. So this is going to go down 2 for every 1, down 2 for every 1. So the slope here is going to be -2. Could we have seen that even without making the table? Yeah, because look at how it was described. It decreases 2 degrees every 1 hour. So all the pieces for every was in the problem, and that's a clue. So that tells us that that was going to be our rate of change. So we had a constant change of -2. We're losing 2 degrees every hour. The y-intercept is when the input is 0. Well, when 0 hours went by, it was 80 degrees in the house. That's when we turned the air conditioner on. So at the beginning, at the start, those are the indicator words that are going to tell you about y-intercept, we had 80 degrees. So our y-intercept is going to be 0, 80. Do I have enough information to come up with the function for the air conditioner? Well, I have a slope, -2. I have a y-intercept of 0, 80. So the equation for the air conditioner is going to be -2x plus 80. Let's look at problem number 2 here. Suppose tuition costs $80 per credit and that student fees are fixed at $50. Give the symbolic, numerical, and graphical representations for a linear function to model that information. So those student fees that are fixed at $50, I have to pay that regardless of whether I take these credits or not. So that $50 is non-negotiable. I have to pay that no matter how many credits I take. The amount that I pay per credit, that $80 per credit, that changes the cost because that depends on how many credits I decide to take. So that's going to be my rate of change because that amount is going to change how much I have to pay the college. So without doing the table first, we could extract the information for slope and y-intercept right from the problem. The word per is our clue that we have a constant rate of change. It's $80 per credit. And the fixed fee of $50 means even if I didn't take any credits, I still have to pay $50. So that's my y-intercept. So that tells me that the formula for how much it's going to cost me at the school, depending on the number of credits I take, is 80x plus 50. Now let's see if we can do the table. And again, we don't have to use our formula, but now that we have a formula, we could use it if we wanted to. So it's a nice way to check your answer. If I take a 1-credit class, let's think about what I would owe the school. I would owe the school $80 for that 1 credit plus $50. So I'm going to owe the school $130. If I take a 2-credit class, I'm going to owe them 2 times $80. So that's $160 plus $50. So that's going to be $210. If I take a 3-credit class, that's 3 times the $80 per credit, which is $240 plus the $50, so that's $290. Now let's analyze this table. Every time my credits went up by 1, what was happening to my cost? My cost was going up by 80 every time. That should make sense because my rate of change was $80 per 1 credit. Graphically, all you have to do, and you can do this one on your own, is again, consider domain and range. Are you going to take negative credits? Does that make any sense? Are you going to pay the college negative money? Does that make any sense? So again, you're going to only show the positive quadrant, and you're going to label credits along the x-axis and cost along the y-axis. And you're going to plot this information just like we did in the earlier problem on this video. So the bottom line of these 3 examples is that you are now seeing that slope is going to be a rate of change, a constant change that you should be able to pick out from the problem with words like per or phrases like for every or for each. And the y-intercept is going to be that fixed cost, something that you're going to have to pay either at the beginning or when the input is 0. So I hope this starts to pull everything together for you. And I will see you in the next video.